Hi guys, I'm Shamanna Sarkar. Welcome to my channel Net Practice for CSI and Net Mathematical Sciences. Now we'll solve question number 7 from part B, 2019 December. This is a question from linear algebra. In this question, a collection of 4x4 real matrices is given named W, and this collection W consists of all those matrices which satisfies this condition. The condition is summation of Aij, where the sum of I and j is equals to k, and all possible values of k are from 2, 3, 4, 5, 6, 7 and 8. Now let us take an arbitrary matrix A from W. So this arbitrary matrix A should look like this. So in this question they have asked about the dimension of W. So a very effective and easy way to find out the dimension of anything is to think about the minimum number of scalar needed to represent arbitrary element of that collection. That means for dimension of W we need to find out the minimum number of independent scalars needed to represent this matrix A, and whatever the number is, that will be the dimension of the collection W. So let us analyze this condition first. So the possible values of k started from 2. Let us think about the case for k equals to 2. So let us first identify which are the suffixes there for k equals to 2. That means for which entry the sum of their suffixes must be equal to 2. So there is only one possible entry, and that is A11, and according to the relation given, A11 must be 0. So let us generalize this fact. The values of k, 2, we have the entry A11. Similarly, if we take the value of k is 3, then which are the possible entry whose suffixes adds up to 3? There are only two entries, A12 and A21, and according to the condition these two entries should add up to 0. So for k equals to 3 we have a relation between A12 and A21. So for the value of k equals to 3 we have a relation between these two scalar. Similarly for k equals to 4 we have a relation between these three entries of the matrix. Similarly for the value 5 of k we have a relation between these four entries of the matrix. For k equals to 6 we have a relation for these three entries of the matrix. For k equals to 7 we have a relation between these two entries, and for k equals to 8 there is only one possible entry, A44. So now observe closely that from the condition given A11 is 0. So this is basically 0. That means for knowing exactly what A is, we do not need the arbitrary scalar A11, because the entry at the 1 position will always be 0. Then from the next relation k equals to 3 we have A12 plus A21 is equals to 0. So we can easily find out A11 if we know A21. So knowing only one scalar we can find the other. So the relation between these two gives us that only one scalar is needed to identify another. So we do not count one variable here, only this entry A21 will be counted. Similarly, due to the relation of these three entries, one entry can be written as a scalar combination of other two. So one of these three entry will not be counted and other two will be counted. Similarly, for k equal to 5, one entry will not be counted and another 3 will be counted. For this relation 2 will be counted and 1 will be left out. Here 1 will be counted and 1 will be left out, and basically the last entry, that is the 4th position entry, will always be 0 due to the condition k equals to 8. So how many non-zero arbitrary scalars are there? There are 9 independent scalars represent the matrix A uniquely. So for a matrix, if we know the exact 9 independent scalars, we can find the other entries. So for an arbitrary member A of W, we need 9 independent scalars to represent the matrix A uniquely. So from here we can say that dimension of W is 9. So our answer will be option number 3, 9.